So welcome to the new video. So um, in this case, we're going to be continuing again from our video that we did on similar triangles. Now, if you remember from the last video on similar triangles, we looked at the idea that when you've got two triangles that are not necessarily of the same size, but have the same shape and their angles are congruent, which means they're in harmony or agreeing, or in simple terms, they're actually the same. The adjacent angles are the same in a sense. So I'm not sure if I just said the right term, but yeah, but you get what I mean. So these are other similar triangles. So I hope this will explain the concept in an even more nice format. I got these triangles here. So I'll try and expand them. So in these three triangles, we're still going to look at the similar triangles again, analogy. So from these three triangles, remember that I said from the last video, I said draw triangles. In a sense, you could have just drawn, I said draw lines like this, two lines that are meeting at 90 degrees, connect them together, draw other two lines that are bigger than those ones meeting at 90 degrees or longer than those ones meeting at 90 degrees, and then just kind of connect them. And then once you've connected those lines, I said label these A, B, C, and then D, E, F. And then in a sense, I said go measure this side, measure that side, measure this side, measure that side, and then divide, sorry, this is DE, divide DE by EF, and then this should be exactly equal to AB divided by BC. I said go and do this experiment, and in fact I said you can do it for all the possible ratios here. There are three possible combinations of ratios here for each triangle. You can divide DE with EF, and you can also divide again DE by DF, and you can also divide again EF by DF. So those are the three combinations. You'll see there that once you make those three combinations, almost all ratios are accounted for, the possible ratios that you can get. So this is also going to be very important, what I'm saying here. So let's clear this up and then do something very, very nice. I'm sure you enjoy what we're going to do. So what we're going to do is this. Let's look at these triangles here. So I did something very, I took these triangles because that's the experiment that I wanted you to do in the last video. So I took these triangles, and then what I did is that I measured these sides, but then of course the scaling is going to be different with me because I'm using a computer. So when I scale in, then the sides are going to be longer. When I scale back, they're going to also be a bit smaller in terms of measurement or the distance, the unit distance that they take. So, but then when I was measuring them, they were, you can also measure them. Of course, you probably get different values to mine. You can pause the video, measure this side. But when I measured, what I got was this side. I got 14 millimeters, and then there I got 26, and then here I got 24, I think. And then this side here I got 17, I got 35, and I got 34. Sorry, that can't be 35 and this be 34. I got 30 here. And then this side here I got 40, and I got 35, and I got 19. Sorry, just want to use different colors here to make this look appealing. So let's take a different color. Let's take green here. So we have 19, we have 35, and 40. And then if you go and divide these ratios, what I got was 1.7 here, I think it was 1.74, and then here 1.78, and then here it was 1.81, I think 1.81, something around there. And then here I got 0.9, 0.89, and then I think I got 0.88, and then here I got 0.5, I think I got 0.5 again here on the dot, and then somewhere around here I got 0.5 again, 5 something, but then I'll just keep it on 0.5. Now you'll notice something here that we spoke about when we spoke about similar triangles. We said these triangles are similar in a they have a special trait. So in a sense, when you divide AB by BC, that should be equal to DF divided by EF, and then which is also equal to GH divided by HK. And you can see here that that is the case. Look at this. These shows that these ratios are exactly the same. This is what the experiment or the practical was supposed to teach you in that previous video. In case maybe you had some troubles while going over that practical and learning this concept. So also here, if you look here again, here is a nice representation, and then we can go choose more colors. Oh, looks like a very limited range here. Okay, here's another nice one. We've got brown. So also here, this is 0.55. So we can see that the proportional the ratios of the proportional side are the same. You have this side, you have that side. Divided by this side, and you divide this one by that one. You're taking this side here and this side, taking this side and this side, taking this side and that side. When you divide them, the same, the ratios are the same. So this is a very special trait of similar triangles. And in a sense, this is what's so brilliant about mathematics and nature, is that sometimes these are developed in abstract terms, but then they get some mysterious consistency that you can get out of this that is just intrinsic into these shapes. Some of them cannot even be explained. They are just intrinsic into the shapes, and then you cannot philosophize them or do anything. That's the beauty of mathematics. So in a sense, now we can go on and say, well, now that we understand this concept, there is something very nice also here that you see, is that this here is for, I'm going to call this x, I'm going to call this x, and I'm going to call the next triangle y, and I'm going to call the last triangle z. So I have x, y, z triangles, and you can see here that these ratios here are for x, and these ratios here are for y, and these ratios here are for z. Nice. So those ratios there are for z, and you can see something here that it doesn't matter how big I make this triangle, as long as these angles, internal angles, are congruent, as long as they agree, then the ratios will be the same. The ratios of the proportional sides will be the same. AP over BC, DE over EF, and GH over HK will be the same. Similar for the other ratios, be the same. And this is a very nice trait because it's also very important in trigonometry. Now that you can see, I can add a fourth angle here, add a fifth one, draw an angle as I don't know, I could draw a triangle as big as it can get. It could be like what? It could have this side maybe 1 meter, and then this side take another value, another side take another value. As long as these are the same, then that ratio of the triangle, when it comes with and in comparison with the ratios of these triangles, it will be exactly equal for the proportional sides, regardless of how big that triangle is. So now we can get some. So now we're seeing something here because I want you to look at something here that we have a DE over EF, a DE over EF, and this DE over EF and this AB over BC and this GH over HK are dependent on something. This angle here, as long as these angles here are the same, and that angles there are the same, as long as these angles there are the same, and this 90-degree angle here, as long as all these angles are the same, then we will get this consistency. So if I change that angle to 70 for one triangle, then they won't be the same, the ratios of the triangle to these ones. If I change the 61, they won't be the same because this is going to be 61, that's going to be 29. Remember the law that we introduced in the last slide, that sum of all interior angles of a triangle is equal to 180. So in a sense, this becomes very important. That's why I'm emphasizing so much on this, because this gives you a very, very basic fundamental of trigonometry, and it will come in very handy. Now, let's further look down. What does this actually mean? How can we best represent this? Because we see that now the ratios of our sides are dependent actually on the angles. So how can we relate those together? So we are going to call this angle here, that is usually here theta, and we're going to call that one alpha, and then we're going to do something very special. We are going to say that we are going to say that the angle, we are going to say that the ratio that is looking at the ratio that is, in fact, we're going to work with one triangle now, and we're going to say the ratio that is looking at AP over BC. We are going to look at that ratio, and we're going to say that AP over BC, and we're going to give it a certain term, and we're going to call that term tangent, and we're going to call it the tangent of this angle theta. I will explain why we're doing that, and what does this tangent mean. Now remember that I said that these ratios will always be the same for any triangle. So it means as long as theta is the same, this ratio here will always be the same, regardless of how big the triangle is. Regardless, AP can change because the triangle is too big, and BC can change all the time, but that value there, this ratio here, will always be equal to this value here, which determines this ratio here, will always be the same. And that's very important because it's what we've shown here with three triangles, that these ratios, when they're divided, will always be the same. So this is very important, because if that's the case, imagine how many triangles we can draw. We can draw infinitely many triangles that are like this, just by just keep on scaling them and making bigger and bigger and bigger and bigger, and can go to infinity. So then, in a sense, we want to quantify that because it's a special quality of mathematics, it's a special trait. So we can quantify it by giving these ratios names, because they will never change. They'll be the same as long as the angle remains the same. And then we're going to draw a triangle here. Let me draw it in the opposite direction. We are going to draw a triangle here. Let me just get a thicker line. Sorry about that. We are going to draw a triangle here. So here's our big triangle. So it's a right angled triangle, and then it's got theta and alpha, and then it's got A, B, C. Now remember that these values can take anything. As long as theta remains the same, we can keep on making this angle as big as we want and everything, and then what is going to happen is that it's going to be more like we are accumulating similar triangles, which keep these ratios the same. So if that's the case, then we need a way of quantifying this because it's a special quality. So what we are going to do, in a sense, we're going to start quantifying this, and we're going to actually give this side some special name. When we're looking at theta, because we know that these now are dependent on angles, when we're looking at this angle, we're going to start looking at this as an individual angles. When we're looking at this angle, we're going to say that that side there is opposite. It's opposite to that angle, and this side here, it's adjacent. It's adjacent to this angle. And then that side there, we're going to give it a name, and let's just call it the hypotenuse. So in a sense, now you see that we have nice three sides here that we've already defined. So we're going to be working with these sides, and all our triangles going forward, we're going to be looking at them in this perspective, not AP and BC, because this gives us a generalized way of looking at these type of triangles, the right angled triangles, in a trigonometric landscape. So when we're looking at this triangle now, we want to develop some nice features. So here's what we're going to do. So we're going to say, okay, we have three ratios that we can get here. We have hypotenuse. We have hypotenuse. Sorry, we have three ratios that we can get here. Sorry about that. Just want to delete this here. We have three ratios that we can get here. So we're going to start with adjacent and divide it by the hypotenuse. That's the first ratio that we can get. And then say this is equal to. And then we have again the opposite. We divide it again by the hypotenuse. And then that's the second ratio that we can get. The third combination, we've combined almost every side, but we will combine this and this. Then we can have the opposite side over the adjacent side. And then that actually gives us a value. Now we can call this here the adjacent of a hypotenuse. We call it a sine. So we're going to call this the adjacent of a hypotenuse. We're going to call it a cosine. So we're going to call it a cosine, but it's a cosine of what? Of this angle, because remember we wrote all this side relating them to that angle. So it's going to be a cosine of theta. This is a ratio. That's what we're calling it. This is a ratio. We just taken this ratio for any triangle that is this form. That ratio there will always be just a cosine, and then this ratio here will always be a sine of theta, because we're relating that to that angle, and then this ratio here will always be what we call a tangent of a theta. Now I hope that you've learned something very interesting here, because these now are universal, and these are universal because of this trait of similar triangles. We make this universal because of the trait of similar triangles. We want a way of quantifying this, because these ratios will be the same as long as the angles are the same. So as long as this angle is kept the same, these ratios will be the same for that specific triangle. So you can go and do an experimentation now. Look at those three triangles there, and then look at those ratios and write down and say which one is sine, which one is cosine, which one is tangent, and of which angle. Because in that case, the first example there, AP over BC, that is what? AP over BC. And if we're looking at 60, that is what? That is opposite over adjacent, which is what? Opposite of adjacent, that's a tangent. So, but then in this case, it's going to be a tangent of what? Of 60. And then we look at another one. We look at AP over BC. That's an AP over AC. AP over AC. We're looking at adjacent. We're looking at opposite over hypotenuse. Opposite over hypotenuse. That's a sine. And then the last one is CP over AC, which is opposite over the last one is CP over AC, which is your adjacent over your hypotenuse. In a sense, then that's a cosine. So I hope you do get the idea. You can go and do for all those, but then this is a cosine of 60. We can still also take this angle here. We can still take that angle there. This is the nice thing about this, because in this sense now we're looking at what? We're looking at theta. So we can still take that angle there. When we take that angle there, then this side here will become opposite. This is opposite in relation to that angle. And then that side there will become adjacent to that angle. That will still remain the hypotenuse. And then we can go and develop the same procedure, but for that angle. And then we can say there we have adjacent over hypotenuse, which is equal to, and then we have again opposite over hypotenuse, and we have opposite over adjacent. Then we write our equal signs, and then we say, okay, this here, in a sense, this is going to be equal to, it's still the same thing, but then now it's going to be the change. The only change is that this is now going to be a cosine, but it's a cosine of what? Of alpha. because the adjacent and hypotenuse we're talking about is in relation to that angle there. And then again, we still get the same thing. This becomes a sine, but it's a sine of what? Of alpha. This becomes a tangent, but it's a tangent of what? Of alpha. Because there's two angles that determine for us all these nice features. You will still see that also we can look at also 90, but 90 becomes a bit complicated because it's adjacent, because it's opposite to the hypotenuse. So, but then you will see when you look at an angle, at a triangle, that is in a sense on 90 basis, because our basis and our reference will be mostly these two angles. So then you will see once we start doing our evaluations, some nice features there. But I hope that this gets you an idea into the ideas of trigonometry and where trigonometry comes from. And to remember these ratios, there is a trick that you can use. The trick is called, there's a word, it's called SOHCAHTOA. So you can always use that trick. It's called SOHCAHTOA. So, in a sense, you have sine, you have opposite, you have hypotenuse. So sine is opposite divided by hypotenuse. That's what this is saying. Here, there's a cosine, sometimes called cos. The most thing you will see is cos, and then sine will be just S-A-N, and then tangent will be just tan. This is also adjacent over hypotenuse, and then also here, this is opposite over adjacent, and then this is tangent. So this word here will come in very handy for you also when you forget these things. So just remember this, that when you forget what a sine is, which sides to look at when you're looking at a sine of an angle, you're just looking at the side opposite and to that angle and the hypotenuse of the triangle. When you're looking at cos, you're looking at the side adjacent to the angle that you're referring to over the hypotenuse of the triangle. When you're looking at tan, you're looking at the side that is opposite to that angle that you're referring to, and adjacent also to that angle that you're referring to. That's you're looking at that ratio. So I hope this gives you a nice idea of where these come from and why do we use them. That's all they are. There's nothing complicated about, nothing more than this. They are just nothing but ratios. That's what makes trigonometry so special, because we're just starting with nothing but ratios in relation to a right angle triangle, which can possess similarity properties. And then from the similarity properties, we see that, well, if these ratios are always going to be the same in relation to a certain angle, then we might as well just define that ratio by using a specific reference to it, which keeps it constant, because it's always going to be constant in relation to that angle. So we use a variable format of looking at it. And in a sense here, we get very nice identities and very nice definitions that are universal to this concept of trigonometry. But this is all what these are, just ratios, and ratios. And then we are going to expand from this concept, and you'll see the beauty of mathematics, because we're just expanding from ratios, and then it becomes this very big, beautiful field. But that started with the right angle triangle, and it started with ancient Greek people and Babylonians wanting to use triangles to make measurements. And then they realized that the simplest triangle to work with is the right angle triangle. Developed this using the concept of similar triangles. In this case, there are a lot of different concepts you can use to develop trigonometry, but I like the concept of similar triangles. And then from there, you get these trig ratios, and you get an idea as to why we can quantify this and give them constant variable names because of the trig that we defined. So all this become very nice and very wonderful in this landscape. So we will continue again and try to make a few evaluations of this in the next video. For now, let's call it a quit for this one. Hope you enjoyed that.